Is this on live or? Yes, I'll click. Yeah, it's hard to drink water this way. A glass of you. Easier? No? Okay, so should we wait for some more time? So you could. Oh, so you could stay at home. Mistake, you know. So we'll wait for 5-10 minutes. Yeah. Sure.
Hello. I'm Anindita Adhikari. I work in the space of data analytics. So that's about me for a few years now, around 10 years. Thank you.
Yeah,
Hello.
I guess, everybody could just say if they have any exposure to neural networks or not.
Hello all, I am Pratik. I'm a recent graduate MTech from IIT Kharagpur, and I have my background in deep learning for the healthcare application.
Hi, my name is Damien. I am a senior applied scientist manager in Microsoft, and I have written papers on deep learning and have quite a lot of exposure to deep learning in the web space. So I'm trying to learn more about applying deep learning in other areas.
Hi, I'm Abhinesh. I'm interning with a startup here called Inkers. I'm currently Inkers. So I'm currently working on a research project on emotion recognition, and it's on progress. Yeah.
Hi, I am Ankur. I work in Infi, and I have a warehousing experience. For me, ML and deep learning was a hobby till last year. Now I am working in some of the initiatives within my organization to leverage this ML and deep learning knowledge which I have gained over the past couple of years.
Hi, I am Senthil. I work in the areas of signal processing and wireless communication. So deep learning, I'm learning by myself. So that's it.
Will get started also.
You're going to formally introduce me? Yeah. So maybe I can just introduce myself or go ahead. Yeah.
Hi all, I'm Diwakar. I work for Soliton for the past 3.5 years now. In the computer vision domain mostly. So in Soliton, the computer vision team, we mostly solve object detection, recognition, tracking problems. And then we have our own smart camera team as well, for which also we use to support and build applications for the smart camera. So yeah, that is, yeah, and then obviously we all use machine learning and deep learning things. And now we are getting started with NLP as well. So yeah, that is mostly my introduction. So with that, I'll just introduce Nishant also. So Nishant, I think other introduction he can give where he finished his bachelor's and all, but I'll just share my personal experience with him. So we had Nishant 1 year back also with us in the Bangalore Computer Vision meetup, where he spoke about the NLP introduction and then introduction to RNNs. And the session was really well received, and the people were asking more sessions on NLP. And we had 2 more sessions also on NLP side itself. And now we thought we should get him again to talk more about NLP, and he agreed to that, and he's here to speak about neural machine translation. So yeah, with that, I'll just hand it over to Nishant.
Thank you.
Thank you.
Thank you. I have my mic here. Thank you again, Salute on whole team to invite me to give a talk here. And feels very strange, echoing from a small room. Yeah, that's okay. So, okay. Should I sit or stand? Okay. So the topic is neural machine translation. And yeah, so I short introduction. I used to work for IBM Research about till about 2.5, 3 years back, and since then I'm an independent consultant in the area of deep learning and applications of text, vision, and speech. I work across several domains, and I did about a PhD about 10 years back, and yeah, moved to India around 2011, and yeah, so let's get started. Okay. Yeah. So the talk is about neural machine translation. Machine translation means, language have a sentence in one input language, English, convert into another language, Tamil, Hindi, German, Spanish, whatever. Yeah, and that's the problem domain. And I'll start off with a sort of background of neural networks and RNNs, because one that is essential for understanding how the current machine translation techniques are implemented. Second, I also like to share a perspective that I have towards the whole thing, which is a new kind of programming, or if you have heard software 2.0, that term. So we're used to doing rule-based programming. When you write code in Python or Java, or the usual stuff, you write a web application, you write a shortest path algorithm, you're used to more writing a sequence of rules. Whereas machine learning, or what started off as machine learning, is more about writing programs with examples. You're giving examples, you don't focus on the rules inside as much as examples on the outside. Okay, and so it's programming with examples and wholes or parameters. Okay, so that's what I'd like to communicate. So it is useful. So machine learning, maybe it started off as a more pattern matching thing, but it gradually has taken up a whole. It has its own discipline of software engineering around it, and so that's why new kind of programming, and like we have scalars or real numbers in, and on top of that you build lists and sets and dictionaries. That's software 1.0, the traditional one. Here you have vectors, lists of numbers, and then sets of vectors, matrices, sets of matrices, tensors. So, and that's the fundamental data structure. Okay. And the key operation here is the dot product. So having a background in linear algebra, or at least recalling the basics of linear algebra, generally helps with understanding what's going on in these networks at a more semantic level. At the more syntactic level, you can just see the structure, but underneath, it's essentially these operations over vectors. And the key operation, there are number of operations. Okay, so dot product. I also have a board. I need a pen. Oh. So dot product. So I'm just starting from the basics, but x1, x2, right, like this. Okay, what I shall make it x and y, x1 or xi, yi summation. Okay, everybody knows this. This is going to be the fundamental thing we are working. It's like plus operator or star operator that we use, or a list concatenation. It's as essential, and the whole, most of the machinery that you see around is just fundamentally built on this dot product. That's why. And what are weighted sums? So convert this x into a w weight. Okay, then apply wi yi. Okay, simple. what is a weighted average? Weighted average is where the sum of Wi is, okay, or just divided by sum of Wi, okay? So it has this interesting thing that, you can 2y1 plus y2. If y has 2 dimensions, 2y1 plus y2 gives you an arbitrary big number, but you divide it by, you sort of interpolate between y2 points. So this normalization is the key operator. Okay, I'm just, we'll keep coming across this weighted average thing in what are called attention networks. And so when you see there, it's just, so I'm just quickly going through. Yeah, what's a function? A function is a mapping from, given a sentence S, you map it to, this sentence is in English, this sentence is in German. So a function F maps a sentence from here. Our goal is to come up with these functions automatically. We don't want to write the rules for these functions. And neural network or a box with holes essentially helps you automatically generate this. You can, not just neural network, decision trees or just linear regression or logistic. They're all these boxes with holes, and they have their own algorithms of filling these holes from examples. Okay, and so the
translation, really, because the language like mapping cannot be properly, function definition cannot hold.
That's right. That's why you have these relations. So yeah, so a very simple example is child parent of relation. So you can see that P, or not, father of C. Okay, P is the father of C. It's a function on one father. Okay, but sibling have C1, C2, C3. C1 is sibling of C3, three siblings. So it's a relation. So when you don't have this one-to-one mapping, there's essentially a relation of. So it's useful to visualize or model things in terms of relations. One sentence may have multiple translations. So it's best to sentence maps into a set of T1, T2. You can also write it as S1, T1, S2, T2. Okay. Am I just so okay? And why probabilities come in? So we are used when you're writing a web application, shortest path or whatever the standard algorithms or the standard. We are not used to thinking about probabilities. Okay, whereas this whole domain of machine learning and all is built around probabilities. Why is it so? Just a very fundamental question. Why are you forced to think about probabilities and struggle with it? Yeah, it's definitely. That's right. Right. Yeah. So basically, sorry. Yes. So lack of certainty, and these are more natural problems maybe as compared to more abstractly formulated discrete problems. And so, like for a sentence, there could be more than one translations. So not just, so you could just model by the relation, okay? But that's not sufficient. You want to give some weight or score to each of them, okay? And if you know that there are 10 translations, or if you have an image and it can either have a cat or a dog or a car, you know that there are 3 things. So you could model it as a relation, but better than that, you could just say that, the cat has chance 3, dog has chance 4, car has chance 10 or score 10. And if you want to view it in a more normalized between 0, 1 range, you divide the thing by 4 plus 7, 17, and you get these probability scores. Okay, so relations, giving weights to each of the outputs, and then normalizing it. That's how you end up with probabilities. And the same with any domain where you have a number of outputs, you're not sure which one has more weight, and you want to compute in a systematic way how much weight to give to each. Okay, so that's yeah, very simple. If you want to, what is called language modeling. If you want to start a sentence with I, and you could write I am, or I will, or I go. So there are n number of possibilities here, but some of them are more probable, more weight. So you assign weights to it. This one particular. Okay, and when you start working with probabilities, and you maybe read papers or even basic notation, you start seeing these p y given x. Y is the output input. So it's written in a functional style. So given x, you want to get y, but actually it means the relation that for a given x, there could be a number of y's, and each of them has some weight. Okay, and then you decompose them into. So think, should I try to explain what decomposition? So suppose you have to go from here to, the nearest mall, and if you plan that out, okay, so you have to first go down the stairs or elevator, then you have to wait for a cab and then the time taken to reach that mall. So it splits into 3 steps. Okay. Similarly, y given x. Now let me be just abstract and say that y has a number of components, y1, y2, yn, and x has x1, x2, xn. You can, in the simplest case, just say that y1 is dependent on x1 and nothing else. And so if you want to get y from x, you get y1 from x1 and y2 from x2, and so on, and sum up their probabilities. Okay, so this is how you decompose a bigger problem into a smaller. So decomposition is fundamental to our programming style. In any program you think of, you just try to decompose. With probabilities, you decompose things using a bunch of rules that satisfy probabilities. There are probably better ways to explain it, and there are different ways of decomposing it, which will you'll see these as I go through the. So just like you have to go from there to here to that. If you were standing close to the mall, you would just walk, not think about auto. So your decomposition doesn't have an auto. Mm-hmm.
For example, from English to Tamil, we do like in the English is like x1,
Right.
Tamil is y1, y2.
Right.
So y1 depends on x1, but y2 depends on x1, x2 plus also y1.
Yes. So defining the decomposition can be tricky. There are many ways of defining it, and we will come to them there. So not if y1 and y2 are just words, you may not want words y1 to depend on x1. You want pairs of words, phrase to depend on x1, x2. So there's a variety of, and that's what people have developed across years to solve this problem systematically. Okay. So that was the high level background of underlying mathematics. Okay. So I am actually in 2 minds how slow to go, or is this too basic, too fundamental for everybody? It's okay. Okay. So then everybody knows about convolution. Okay. W, X, and a sequence of. Okay, sequence of each is at each place you do a dot product. That's why that dot product is important. And you do a sequence of dot products. So every time you collapse into number, and sequence of numbers as output. Okay. So again, this is some of the motivation of why program with holes, but I'll just skip it. The parameters, I call the parameters the holes. Yeah. So and you have to fill in those holes by an algorithm. Yeah. So maybe if they are coming in, so I like to go back to the programming with holes and examples as I think it's fundamental to the different way in which we should think about it. Yeah, so if you have tried to predict stock markets or even the curve next day, you would know that this thing called moving average, simple moving and exponential moving average, and so on. Yeah, so if you write the formula, simple average is a sum of xt till n minus 1 divided by n. This simple thing. And exponential moving average is more weighted kind of thing. Okay, so these are useful formulas that help you predict. But suppose you want to come up with a new average or new kind of metric that is not easily definable in terms of it, but it helps to predict the next step. So what you'll do is that you'll take these x's and you take a bunch of parameters and put them together in a box and feed in lots of example of if my current x is this, what is the next x, and then expect the algorithm to learn these weights automatically. And the weights that the function that it might come up inside the box could be very new. You may not be able to understand it or interpret it, but it will definitely help you predict. So that's the so here you're writing rules which you think are useful. They are often you think they're enough to predict, but then so that's what happened with images or people trying to classify images or understand sentences or speech to text. We're writing these rules for a long time, 30, 40 years, a huge amount of research, image gradients and various kinds of speech pre-processing, MFCC or whatever. So there are a bunch of rules that people wrote and they pushed the technology to be good enough, but not, well, to be good, but not good enough. And when the neural networks domain, method of programming came, you could, these rules will sort of learn automatically. Yeah. Okay. So so the fundamental operator is dot product plus a bias, and all the operators. So I find it build mental. People must have taught you about convolution networks and recurring in 100 different ways, and you must have read them. But I find it very simple to just view both of them as just for loops. Okay, for loops with holes, and so for I in range of n, where n is the number of say pixels or the length of the sentence, you write a function which essentially the idea is that in a convolution network you can, if x is the input, then you can only access a window minus w plus w around the current position, and you're supposed to compute your output whatever it is by just looking at minus w and plus w. You're not, if you are at this position, you can only view this. Okay, this very rest you're sort of pushed into a space, but thankfully or magically this is enough for a huge number of. For example, if you want to just figure out what the image has a cat or a dog, this is just enough. You can just look locally at different positions, hierarchical way, and figure out what it is. RNNs, you have, it's like a while loop with accumulator. Okay, while I less than n, sum equals sum plus I. Okay. This is your RNN. You have this special accumulator variable. Just remember, I'm not sure what you call it, but let's call it accumulator. And at every iteration, that accumulator is updated with some function of I or some function of the previous value of accumulator and I. Okay. And so by having the sum, you are able to have a view into the infinite past, because sum has in some way captured all the exercise that before, instead of a convolution network where you were only focused onto a window. Okay. Yeah. So having a loop view of both convolution and so essentially when you're trying to, suppose you are trying to analyze a sentence, okay, you want to find the category of a sentence. Okay, buy me a phone with 32 GB RAM. You want to predict that the category is mobile. Okay, so try to do it just this way with CNNs. Okay, what this means, you have to iterate over this. At every point, you can only look 2 steps back or 1 step back and 1 step forward. Okay. So when you look at buy, it doesn't tell you anything about it. Me doesn't. Phone definitely tells you about mobile, and 32 GB RAM maybe is similar. So you'll have an indicator 1 here, the rest of the position is 0. Then you somehow compress that and get a 1. That's that. Okay, so you roughly see how it works. Okay, you essentially trying to find indicators using these. And how do you come up with the fact that phone corresponds to mobile? That's where you use these boxes with features or I'm not sure how to. Essentially, you have a transformer which converts a phone to the mobile category, and that has to be learned automatically. Okay. So, and that's a good question, and that's why this view helps. So wherever you can sort of locally look into the thing and solve your problem, you're good. But where you need the whole history. So for example, images, CNNs, because you could locally detect edges and then combine edges to detect something more, and then detect eyes and face. So the local thing was. Whereas with sentences, you could yeah, I don't have a good example, but suppose you wanted to talk, I want to go to a bank of the blah, 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 and then the word river comes, river. Okay, so when you see the word river, then you know what the bank means, river bank. So there could be a huge distance gap between the, if it was the bank of blah, 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 Barclays or whatever. So that will change the meaning of. So here you need this much of view into the sentence. Or if you are at the river, you need this much view back. And if you have a fixed window, you will not. Either your window has to be huge, which in some case will be not sufficient. So that case is right. So sentence and CNN are 2 different things. So maybe you should repeat your question. Into a mobile category, yeah? Right.
Giving the sense of CNN rather than
yes, maybe because so maybe this simple example tells you that CNN is good enough to solve this problem. Maybe for classification problems, CNNs are good enough. Maybe this is going in the so the problems, many of the problems can be solved by CNNs and RNNs with equal performance and performance. But then the issues become how quick are you solving them, how quick are you learning. So CNNs have some amount of parallelism in them, whereas RNNs have a more sequential nature. You're running a for loop. So that's where the RNNs sort of start performing. If you can do a task well with CNNs, you generally stick to CNN. Yes, yes. So I would say that the first classification efforts were of sentences were done with CNNs. There are several other issues here. I'm just glossing over. Having a word, it could be spelled wrong. Okay, and then you start looking at just character sequences, and then you have to compose these words from character sequences. All that could be done inside the framework of neural networks and CNNs, and that's where a lot of effort is spent if you want to analyze general, real world sentences or Twitter feeds, for example. Yeah, but CNNs are quite powerful. So I just wanted to make you have a unified model for thinking about CNNs and RNNs. Both are for loops. One has an accumulator which keeps track of the infinite past. Here you only have the small window. Yeah.
My assumption till now was like CNN is something to do with image
Right.
CV, right? So are we saying we can apply the same CNN techniques with NLP, maybe when we have some very limited results to apply?
Yes, when to apply is a tricky question. It's not straightforward. So you can apply CNNs to natural language or speech, which has more than. You can apply RNNs to images also. Nobody stops you. There are a lot of people who have done that for different problems. So classification is just one of them. There are other segmentation problems, for example, with image, where you need to know the sequence, need the characteristics of the sequence more properly. That's where RNNs are more useful.
Okay. So the popular culture says RNNs are for NLP and CNNs are for image.
Yes, that's the
Probably
sort of
research space. Things are like very much
Yeah, even in practice, people.
line is blurred. Probably I would say. I mean, in research space, you are saying we can apply both techniques in
That's right.
both areas.
Right.
But in the popular cultures, or maybe right now, what we are saying in the market, or maybe
Yeah, so
we are.
So the gap or the twist or the contrast or the fight between CNN and RNNs has been long, and it will continue from. There are several other reasons why you could both can be interchanged in them. And CNNs have a sense of parallelism. If we went detail into the construction of CNN, you'll see that there is a parallelism there which you can exploit. Whereas with RNNs, you have to have this accumulator. Once if you haven't computed the accumulator in the previous step, you can't go to the next step. Okay, so that makes it sequential and therefore less efficient. But it can this nature of function can actually solve a whole bunch of new problems that and this narrow view cannot. Okay, good. So I have. So how do you fill in the holes? So these holes are these F's here. Okay, I've just, and this function, how do you write these functions? These functions eventually come down to just this, some form of linear transformations plus squashing or a sigmoid-like thing, or things which squash up large number lines to 0, 1 region. The combination of these and nesting of these are what generally functions are. And the holes are the W's and B's. You don't know what linear transformation and what B to apply. And these are learned from examples. Okay, so how does it work? You provide a bunch of examples. I'm just covering machine learning 101 in a sort of convoluted or a different more programming kind of approach. Okay, so you provide a bunch of examples. For example, for image classification, you provide image cat, image car, image tree. Okay, these are a bunch of examples. Provide a bunch of them. You set up your function inside the box with a bunch of holes, and then you start predicting. Yeah, whatever the value of my W and B is, you predict something. Find the diff. If this is the image, I expected a car. I'm getting a dog. So diff, update my W's, update my holes, and keep continuing. If you have huge amount of data, you'll eventually learn these patterns if everything is good. Okay, so that's the principle of learning from examples and holes. Yeah, and the examples, the process of providing examples or different kind of examples is called supervision. There are 100 different ways of supervise these problems. And yeah, so for neural translation or translation problem, provide parallel pairs, what are called parallel pairs. Input text in English, output text in German. Okay, or whatever. You provide a huge number of them, and your machinery learns from those examples. Okay, there's one important factor, which is that to learn these functions have to be differentiable. Essentially, how do you say? The idea is that if you're very simplistic, if you can draw your function like a curve, then if you start at this point of prediction and you realize that you're wrong, you can just go down by the gradient of the curve and get to the right point. That's the simplistic 2D idea. But your data points are high dimensional. Images have like 256 cross 256 points. Sentences also can be embedded into so there's a huge space, high dimensional space, where you're supposed to start predicting from some place and gradually go down to the right place where the parameters are right so that they predict the right thing. Okay.
How many neurons are there in your model? So what do you mean by how many neurons are there?
Right. So there is this. So people, when they started talking about building neural networks, they and even now they work with analogy with brain neurons or what. Yeah, but when they were implemented with computers, they looked more like W's and B's. Okay, so when you draw a graph with a bunch of this layer and they're connected by that, those edges are essentially the W, the weights which transform this layer to that layer. And you take a layer, the number of points it has, those are what are called the neurons. Yeah, so yeah, you can just think of the length of Y, the length of X. Each element is a big. Yeah, so each element of that array is what is called a neuron. Okay, this is just to show you I mean, I guess most of you are familiar with how deep learning has taken over almost every, at least programs around images, speech, and text. We weren't able to write good programs maybe till 7, 8, 10 years back, as well as we can write them now. And this revolution has taken place due to very, very quick research based on these simple, learning from examples, these convolution recurrent primitives. And essentially the approach has changed from when you were writing the rules to figure out where the mobile is or where the cloth is, to letting a network figure out the rules itself. That's the main shift in mental paradigm. And just an example of an image classification network where each node is these blue nodes are the convolution nodes. Okay, there are a huge number of. So you start with the image here and do these local operators, compute something, and then you do them again and compute more and more abstract features until you have figured out the right set of features that will distinguish whether the image has a car or a cat or a dog. And to work on huge number of categories that you see around the world, so many layers are required. That's what the several years of, at least 3 or 4 years of empirical experimentation taught people. That they started with a network this big in 2012, and then they figure out why it was not doing well, and they kept adding. There are sub patterns inside this network. Oh, the inception module is this. See this module being repeated everywhere, and this is the reason why that particular structure was designed to help you discover these features better. Okay, so that's just so this is the inception module, which has a bunch of convolutions of different kinds. So the weight or the convolution, you can have a bigger window, smaller window, rectangular, square, whatever. There's a number of choices here to design these networks. So it started off being in software. There's so many libraries that do it, but in hardware also there are implementations now. For the past few years there are. Okay, and one of the reasons I want to make it faster, so implement it directly in hardware. So FPGAs are one of the more flexible ways where. Okay, so we'll be focusing on RNNs, recurrent neural networks, because we want to the sentence we may have to look up a word which was long back before, and yeah. So mathematically, the same while loop that I wrote, sum equal plus equal to I, is can be written in this way, where HT is the current accumulator, hidden state, X is the current input, I, and given HT and X, you compute the next hidden state. This is a very simplistic but almost full coverage representation of what RNNs do. And one way to implement F would be multiply HT by a vector, by a matrix. This is a transform it here, transform X, add a bias, apply a squashing function. Okay. We could spend a huge amount of time thinking why it is designed this way, but we have to cover a lot of ground today. So let's see, they're just transformed linear transformations of HT. So HT and X are in general vectors. So I'll come to, so images, you can think of numbers or matrices very easily. An image, take every point, the intensity at each point, and convert in number, and that's it. Sentences, words, you have to figure out a way to convert them into vectors, because the rest of the machinery works on vectors and tenses. Okay, so there's a way to convert words into vectors. So once you have a vector for a word and a vector for the accumulated sentence from the left, you can transform them and compute the next element or in the sentence. Yeah, maybe at this level, yes, but depending on the scale you are working on, you will have to concretize X into what is the element of interest. But nothing stops you. Any sequence of elements. It could be images also. You need not, or speech. Speech also, RNNs are a fundamental operator in analyzing speech to text. Sure. Yeah, you can ask your. That's right. So that's one of the problems. It's called language modeling, and so till now, so the talk is going to be about machine translation, which we haven't got there, and that there the problem is, given an input sentence in English, you have to convert it into German. Because that's the problem we are trying to. But the basics, the machinery involved is common to the problem that you said, predicting the next word or image classification. That's why I'm talking in more general. Okay, so again, we could just spend a lot of time figuring out the different kinds of recurrence. So essentially, this F here is a box which takes in HT, the accumulator sum, and the current input X. And the way you design this box, there are 100 different ways, and people continue to write papers about how to design these boxes better. Okay. So two popular representations, one is called an LSTM, other is called a GRU, long short-term memory gated recurrent unit. Okay, these are two popular implementations of F, which are pretty ubiquitous. Everybody just, and there are libraries that provide you this implementation. You can just start off with a block of LSTM and GRU. The inside structure of an LSTM or GRU takes a bit of belaboring to understand, and yeah, and I am not sure whether I should go into it or not. Essentially, you have you want to get to the next state HT. You have the previous one HT minus 1, and to compute HT, you do a bunch of transformations inside it. Essentially, the idea is that you do a weighted average Remember the weighted average that we talked about in the beginning of ht minus 1, which is previous state, and a candidate new value. Okay, and what are the weights that there's a z, that those weights are also computed. So this is the f function here. Okay, it takes in you won't see the x right here, x is somewhere there. It takes in ht minus 1 and x is somewhere and computes the ht. And to compute this, you have to figure out where z came from and where h tilde t came. And there's a whole machinery to compute. Essentially, the idea is to compute z and h tilde, you combine again ht minus 1 and x in different ways and apply squashing functions. Okay, so it's a vector, it's a hidden state. You can just remember the accumulator that we had. H generally comes from hidden state. So the LSTM or the RNN just starts with some accumulator state and the vector that keeps improving. Okay. Layers in the sense. Okay. So yes, I mean in general we'll have hidden layers. There's also a little bit of confusion about which direction we go with. We can go in two directions with hidden layers. No, so it's not the weights, it's the input. It's a sort of representation of inputs. So I wrote this function as a very simple while loop. Sum equals 0, while I is less than n, sum is equal to sum plus I. Okay, you could just generalize it to sum equal to some function of sum and I. So sum is h, the accumulator. So it's the interface between two blocks. That if you could view it that way, the box has the weights inside it. Okay, the weights are inside this f. How do you transform a sum and I to the new value? But what comes out at every stage is sum. What goes in is x or I. Okay, and just jumping to the x's or the i's are the words here, and h's are the sum are the vectors that sort of represent the compressed representation of the prefix of the sentence. In any sequence you're moving, you can just sort of compress it to the current h. Sorry? Yeah, so it's xt here. In the diagram, probably it's missing. Yeah, it's probably missing. It should feed in from somewhere because yeah, it feeds in here, it feeds in here, it feeds in here, it feeds in everywhere. It's just, yeah. So again, I have copied these diagrams from all over the web, and I have to thank, I couldn't just cite every slide with, but thanks to numerous people. So there's papers, but the learning in this field or the research has become very democratic. People have written lots of blogs and articles to explain and distill it even better than the original papers. So which actually helps us absorb and digest this in a more layman fashion. And that's something that is very peculiar that didn't used to happen as globally 10 years back. So there's also a learning revolution that happened. So anyways, yeah, so x is, so maybe, so x, yeah, these boxes are the weights here. X and ht minus get combined into what is called a reset gate. X and that reset gate and ht minus gets combined to the candidate h tilde t. And then you use this h tilde t here. And these weights z are also obtained by combining xt and z. These boxes are W, some weight matrices that are unique to every position. Okay, we could go into a huge amount of depth there, but let's keep going. Yeah.
It also looks like a kind of constant thing where we take some updates and try to combine.
Yes, so basic autoregressive or basic recurrent equation, just this. This has huge number of a huge number of real life phenomena have been captured as this. Kalman filters is one of them. Okay, and yeah. So what happened, a lot of things which were, Kalman filter is again an example of handwritten rule, which was found to be very useful. A lot of those operations were now, converted into using RNNs. People started using RNNs where they didn't know what's the exact operation happening inside, just in terms of these weights. It's something, but it generally started giving performance equal to those filters or even better.
Kalman assumes some system model, I think.
Right.
Then it uses it like based on the system model output and the measured output.
Right.
But here it's like there's no system model as well, it's learns.
Yes. So here the system model is given by the samples, input and output, and whatever the weights are inside, the input and output of the system is the input is a sentence, output sentence, input image, output class. So those are the only supervision you're giving it, and you're expecting these machines to learn the proper weights values here. That will, yeah. So essentially, what is happening? You are taking a real life object, an image or a sentence. You are mapping down to vectors or sets of vectors, trances, and then you're doing a bunch of geometric transformations. These W's, multiplying it by W's is geometric. The bunch of scaling and rotating, and if you do it in a proper way, you'll get a representation of these vectors which are more amenable to what you want to represent output at the end. Okay, so instead of working on lists and sets and dictionaries and manipulating them as we do in usual programs, that was software 1.0, we work on vectors and transform them geometrically, in very complex ways to get to the desired output. Okay, that's the summary. So the problem that you were talking about, language modeling, essentially, if you have the sentence, the cat sat on the mat, okay, and you have generated this prefix, the cat, and you want to figure out whether the next word could be sat or not. So you write it down as the probability of sat, as opposed to you could also have a word on after this, cat on something, and there's probability of that. So that's the probability of generating the next word, is the problem of language modeling. And again, so how do I explain this? So the idea is, so the idea is that you have written cars here, you just think that these are words. So you take in the first word, maybe, okay, there are 3 layers or whatever. You just assume that the cat is the thing that is being fed here. And so the first level just takes the word the, it goes next level, then the cat word feeds in, then some other word feeds in, and at the end you predict the probability of the word sat. Okay, I don't think this is a good, for some reason I thought that this was a pretty good representation, but let me come back to this. I also had so I think it's important to first, so we'll be talking about sentences today, translation sentence, and yeah. So I just told you that you have to convert everything in this world of vectors and tensors. How do you convert a sentence into a tensor, a list of vectors? So it's not a trivial problem to do at all. And there are, again, 100 different ways of doing it. I'll tell you a very quick and very popular way of doing it, which is not what is written on the slide, so that you start getting some intuition. So suppose you are talking about news articles and you take, ndtv.com, you take all the words on the article that you have. So you have word, India, government, democracy, whatever. You have a huge corpus of words. Okay, now you get a sentence that, GDP grows by X%. You have to convert this thing into a vector of numbers. Okay, sentence, it can automatically decompose into words. So if you can convert these words, you're done. You can just concatenate put them together. Okay, how do you convert GDP into a vector of numbers? So maybe right. Sorry. That's one way. That's called character level representation. So you can encode each of the alphabets into 0, 1, 2, 26 or whatever, 30, 50, and then just replace them by the numbers, and you'll get a yeah. Right. So that's what I'm coming to. Yeah. The problem with this character is that it depends on the length of the word, variable length, which can get you into problems later on. One more naive. So that is one naive way to do it. Another naive way to do it is just to collect the whole set of words that you'll be dealing with, assign numbers like a dictionary count to. You call this 1, call this 2, call this 3. Okay, so you'll have this word 10 and 20 and yeah. And again, these numbers don't represent, there's a better way to represent it. If you have like 200 words, you will have 200 length vector. And if GDP is there, set the 1, all of them are zeros. Grows, take the vector, 10th position to be 1, the rest of them are zeros. Okay, this is called one hot or term. Okay, there's a TF, IDF term where instead of just having a number, you count the frequency of the words and then normalize it, whatever, and get the number there. The rest of them are zeros. Okay, there's a bunch of ways people have tried and used them for the usual set of problems, including translation in the past. So yeah. So more recently, so the problem with all of these is that these are very syntactic. You don't, by looking at these numbers, looking at the number for GDP and looking at the number for economics. Okay, this number will have 1 at 14th position. This number will have 1 at 102 position. You sort of, GDP and economics are sort of similar words, but you don't have any sense of similarity looking at the vectors. So these vectors don't actually capture the semantic meanings. Okay, so this is a huge drawback. And in spite of this drawback, people have used this representative for many tasks very successfully. Word embeddings are an approach to resolve that problem. Okay, essentially the idea is that I won't tell you again how it is computed, but I'll tell you the basic principle of it. So if the word GDP and economics, if you look at these documents, you'll find maybe these two words occurring nearby. Okay, so a word is defined by its context. Okay, so to represent a word as a vector, we'll choose these numbers, x1, x2, x3, x4, such that, so come up with these numbers somehow, okay, for economics, so that these two vectors are similar. Okay, and what does similarity mean? So similarity of vectors is very well defined in linear algebra. It's the dot product divided by whatever, but essentially it's defined by the dot product. So that's where we gain by mapping things to just pure vectors. That now you can use the basic operators on vectors to define similarity. Okay, so how? Yes, so I just simplified it to the, but the essential idea is you find the vectors so that they are similar. Similarity is defined by dot product. Okay, and so you have the whole corpus or a whole set of words, and you come up with these vectors in a particular way that if two words are occur nearby or are in occur nearby is the key principle, and similarity derives from that. So generally, if two words are similar in large pieces of text, they'll happen nearby. Most cases, again, that's generalizing, but yeah. So you come up with these vectors in this way, and you call them word embeddings. Okay, you could call them word vectors also. So the benefit was actually it's on the next slide, yeah. But the benefit I already told you that the vector for GDP and the vector for economics, if you take the dot product, the value would be high. They will be similar. It actually lets you use the machinery of vectors and linear algebra to model sentences. So sentences are strings of words. Yes, so compared to the default, the character-based simple 0-1 modeling, this definitely improves. Yeah, so yeah.
One example is basic arithmetic. You can do arithmetic with words. So it's like father minus boy, or you can do arithmetic, basic arithmetic.
Yeah. So
minus apple.
So this slide is there's this very systematic way of computing this vector, which I'm not covering. But if you have the vectors, you have a vector for man and woman and king and queen. Subtract. So subtract woman minus man, and you get a vector. Add that to king. You'll get queen. So it's that powerful. So these words which earlier the computer didn't understand, it's able to figure out because of these special representations.
You have to use a multi-dimensional space there, right? A semantic space, just you model them and then you put all these words.
Yeah, so you set up a constraint solving problem where you say that if these two words occur nearby, then the vectors should have a high dot product. And you maximize that dot product for things that are nearby and minimize it for things that are far away. That's what, this technique called CB, or a continuous bag of words. There's a neural network-like structure which predicts from the context too. And there's elaborate theory. There are many different ways of computing this. So we are sort of, each slide is multiple years of research, and still there are people who are coming up with new ways of computing better word embeddings, which capture, so dog is an instance of animal. Okay, so your, or a better example could be, okay, so maybe the initial way you used to compute the word embeddings didn't capture the property that dog is an instance of an animal. So dog and animal vectors were still relatively far away, and not as much as you wanted. But with more improved techniques, you can have improved similarity in the sort of taxonometry and all that. So there are, language and words are not simple to define even by human beings. We have been trained many years to do that. To train computers, there are a huge amount of effort required to let them understand. And word vector is the starting point. Yes. Yes.
It will be a cluster type of.
Yes. So all of them, there are many clusters, and you can go deep into the cluster and see. You'll find things that you may not want chair and table to be together. You may want chair and a seat to be together and table to be far away. But some cluster will have chair. And so the process of generating those clusters is pretty complicated. But yeah, that's the space we work in. It is again the so it's not separate. It's fully embedded into the same machinery that I've been talking about. You train these vectors using examples. Examples are words which occur nearby and words which occur far off. So you want to improve for words happen nearby, and words that are far off, you want to reduce the similarity dot product cosine.
That happens before, for example, if you want
yes, so right. So that's also a good question. I'll just confuse you and say that it can happen before if you want, it can happen together with translation if you want. So you can set up since that is also a sort of neural network, a very high level intuition. This is also a neural network that computes this. You can compute it separately and take just the outputs and then work in a decoupled way, or you can just join the neural network with the final thing you want to do and do it in what is called an end-to-end manner. That's where the end-to-end thing. So these are very natural questions that come up when you try to decompose these big tasks into a smaller piece. And each of these units being so heavyweight already, and there are 15 different ways, when you practice, when you try to implement them, the huge number of choices there, and you have to make good choices based on your judgment. Right. So I will hold that question. So one way to use these things. So when people initially trained these vectors, they trained it for huge, like Wikipedia size, which is supposed to capture the whole meaning of the word or whatever. So, and then they collected these word embeddings and publicly opened. So word vectors, a thing called Glove from Stanford. After that, Facebook has fast text. And then there are even more recent embeddings which are. So these are all embeddings computed by similar algorithms, but the vector in one representation may not be exactly the same as. And you could pick any one of them and start off with your, for example, the classification task that we're talking. You convert each of the. You have to first convert. You can't talk to a neural network if you don't convert a string word into a vector. So you have to pick one of them and start. Yes, so there are embeddings, or there are, if you understand, the embeddings which specifically capture those structures. For example,
one is hierarchy is already right. For example, we have like balance,
Which word vector presentation? I don't think it will, because
it will capture it to some extent.
in the word clustering,
So you look at like different embeddings, you capture it in different extents. It's not like if you just train word of conversation or something, you will actually see this. When you use vector map, you will actually see it.
so my question is like, it's based on similarity, so it will definitely form some sort of a cluster. But does it, is there any word vector representation?
So so let me just, all representations will have clusters. There's no representation that, again, cluster is an artifact of these. You just group them together nearby. But so that's just the visual representation of it, or where they lie in high dimension. Whether they capture similar meanings or not is a completely different question. And for that, you have to look at these vector operations of similarity, capture them. And some of them will capture the meaning better. Some of them will capture one kind of meaning, like taxonomy, better than other. But they will lose on some other front. And to get all compassing is still an open problem to get something that is. So again, there's a huge variety depending on how much capacity, how much expressiveness you want. So you start at maybe 50, go up to 2000, and 2000 bits or 2000 numbers, vectors for each. So the 2000 vector will capture a huge number of properties. You can think of sort of, it's not that way, but each bit captures some dimension of meaning. So whether it's a capital, whether it's a man, a human being, you can think each of the bits. That's not right, but intuitively. So if you have 2000 dimensions, you're sort of capturing 2000 different aspects of this world in there. So again, maximum dimension required depends on the problem you want to solve.
What they have done.
From 50 to 2000. 2000 is one of the higher ones. Generally, people stick with 300. But again, these numbers I don't think mean much. You're solving the problem doesn't really depend. It depends on several other things besides the dimension size. I'm right. Yeah. So there's a task, a concept of a task, which is whether you want to classify a sentence or translate a sentence or label a sentence in particular. These tasks can work with 50 or 300 or 1000. And to improve on that task, the dimension may not matter. Something else will matter. The intermediate network will matter. Okay. So LSTM we talked about. By LSTM is another very favorite animal that roams around. And the idea is that you can do the for loop, you can go left to right. Okay, keep adding. You could also go right to left. Okay, and so you start with a vector, whatever. The sum is a vector, and you see a word, you update that vector, update. So that's what. So so this example is at the character level, not the word. So you have this word genetic. You look at the individual. Each thing gets converted into a vector. Okay, E gets connected. You see, these are unique vectors. Like you could get them, from a public source now. Now you run a while loop over them. That's what a LSTM does. So this is one LSTM that runs. You start with this, what is called a hidden state. There is a starting sum equal to 0 state. You take this vector in, you apply those W's, whatever I showed there. You get a new vector for after G. After E, you get another vector. At the end, you get another vector. Okay, and each point. So at this point, the vector sort of summarizes the meaning of G, E, and N. Okay, at this point, it summarizes the meaning of G and the set of characters. Okay, so this sort of, you're composing the meanings from the meanings of characters. By meaning, I mean the vector for it. You compose the meaning of the word. So this thing represents the word, starting from the meaning of the. Does that make sense? And similarly, you could go right to left. And you could start with the 0 vector here. And then what do? You take these two vectors, which are, this captures the meaning left to right, this captures the meaning right to left. And sort of you have more meaning together than individually. So you put them together, concatenate them. Okay, concatenate is just another standard vector operation. And then that is what you call the word embedding. Okay, so from characters to words, you could go in this way also. So till now, we have been talking directly about this word embedding, and we can directly compute them. But we can also start from characters and get here through using this. So you see why the while loop is so important there. All of these are sequences. You can chunk it in anywhere and run a while loop over there, compute a representation. And then you can do that hierarchically. Okay, and there's something in between the character and word also called a subword. You could just take gen, have one representation for it, etic, have one, and then compose them. And these subwords are also important when you encounter very new words which were not in your dictionary. Okay, so yeah, so genetic came from here. Similarly, you have a human and a disorder. This is the sentence you had. Again, there is a LSTM that runs here, which composes them, and you get a sentence embedding. And there's something called CRF, which you can use at the top, but this is good enough. So one way you can use it is that if you want to categorize this sentence into medicine, say human genetic order, you can compose the embedding. You can get the front and the end, put them together, get a vector, and say that this is the vector for my sentence. Okay, I have compressed the meaning of the sentence into this vector. And now I'll use this vector to classify. So I will transform that so that I'll get output medicine versus output mobile. So I'll have two outputs, medicine and mobile, and medicine will have high probability once you start from that way. Does that make sense? So that's the end-to-end thing. You start from these basic representation of subword or character units or words and transform them mostly through LSTMs and get the final sentence embedding. I mean, this is one particular way of getting the embedding of a sentence. You would do it in several other ways. Yeah.
G and predicting, we are going towards right side. First line, okay.
Yeah, so
G are predicting E, right? Kind of.
you could, so yeah, so what I was talking about is a different task where I want to take this sentence and predict medicine because the category is medicine, as opposed to mobiles, which were, yeah, and to do that task, that is different from predicting genetic given human.
Yeah.
That's a different task. Okay.
I was trying to understand why you.
Yeah. Okay. So by okay, go, maybe you should ask
Yeah,
the
so
question.
basically when you go one direction, from after G you're predicting E and then to V you're predicting L and like that, right?
No, so you're not predicting; those are given.
Yeah, given. Right.
Given. Yeah.
So when you do the reverse order from C, you are kind of going
Yeah.
I and all.
Yes, and the idea is that you can, if this was a sentence, it would be more. So the bank and the river thing. If the river happens there, you can maybe get the meaning of the sentence earlier if you start from the right. So that's the intuition of why you go in both ways.
Notation of that 3 dots converted into 2 in second step. Yeah. First, the color code, say for G. 3 capital whatever.
The
First layer.
first layer, the three bits, 3 dimensions.
Then how it's compressed to 2.
That's a choice. So the sum and the x's. These are the x's. This is sum. Okay, sum you could represent it by n length vector. This you could represent by m length vector. Here m is 3, n is 2. You could have made this 24 also. Okay, how do you come up with these numbers? Mostly empirically. People have been trying to solve problems for a long time using these, and they have figured out these right dimensions. I don't think there's much theoretical justification of why. Yeah, you'll see all sorts of numbers. Generally, the hidden, this is called a hidden layer. Okay, because it captures the summarized accumulator, and the 512 or 1024 is the typical representation for this layer. If it meant to the original author, I just copied the figure. Yeah, so my idea is just to, yeah. Okay, so we are now very close to starting on machine translation. And I wanted to, yeah, so one, now I'm maybe jumping and I don't know how to correct. One popular, yeah, so the philosophy or the understanding is that when you have an image, switching to image, because there are many principles that apply. So you have this 256 by 256 image, those many pixels, 256 squared pixels. The core information in the image may not take those many pixels. Yeah, it's just a representation that we are familiar with, we can observe. If you have to really compress it, it would be very small, much smaller. And this sort of dimensionality compression is the principle behind, sort of this whole field. Okay, so one way it is exploited is that you can take the original image and transform it into what is called a compressed latent representation. Okay, and then try to recover the image from that representation. And this particular architecture or the way of doing thing is called an autoencoder. So it's not just image. You could take a sentence here, try to regenerate this. A sentence converted into vectors, tensors, sort of gets compressed into a very, and then this has enough information to regenerate the same sentence. This principle is, I'm not talking about an application. If I, what's a quick application here? PCA is similar. Captioning is a instance of translation task, which I'll come to very quickly. Label. Okay. So yeah, so this part is called the encoder, and I'm introducing the encoder and the decoder now. So let me, yeah. So the previous slide, you could sort of think of this representation as the compressed representation for whole genetic. So if you just naively represent it, this genetic would be represented as a list of these vectors, or a vector of length 7 to 321 bits. But through this machinery, you can actually compress the information to a very small number of vectors. Okay, this, and I'm not saying, so there are many, so this compression would be in general lossful. You would lose some information. But again, if your problem requires, you would want to design the network in the way that you don't lose any information. Typically for the classification task, you don't need the whole information. Maybe genetic or disorder is good enough to tell you medicine, or some part of genetic in there. So you don't need always, you just need part. If you want to classify an face, with the face there, you don't need the background or whatever. You just maybe need the eyes. 2 eyes are good enough to tell you. So there's many tasks just require compressed information to be successful, and this is where, so in general, so the encoder decoder architecture, so the autoencoder architecture sort of tries to compute a representation which is good enough to regenerate the whole thing. Okay, a slight modification of this architecture is the encoder decoder, where you compress and find a representation so that you can map it to something else. So for example, with images, if you take a satellite photo or Google map, okay, that's what you feed in here, and here you want just the roads in the, so that's a subset of information there that has sort of a one-to-one corresponding with the actual thing. Okay, and so this architecture now helps you translate from one domain to another. And now that you understand how you can translate from image to text, which is the image captioning thing. You can translate from speech to text also. So all sort of translation can be done in this encoder decoder architecture. It's a huge, very powerful architecture. Yes, and very differently. Again, the building blocks will remain these RNNs and GRUs, but the way you interact them, the way you number of layers you add, number of abstractions you compute, they'll be very different. So okay.
Common latent space cannot be getting the difference. Based on the problem, what you are end goal, the way you create your latent space.
That's right. That's a very so people do try to compute a common. So there's a task called visual question answering, where you look at an image and ask a question you want to look at. So if you work in the common domain where images and text is embedded in the same domain, it becomes sort of easier. So people do try to do that. It's a more hard problem.
With the Google image, what you have the satellite image, if I'm trying to find roads,
Right.
the kind of latent space might be, the way I have created latent space is different than when I try to look for rivers or something.
Yes. So I mean that statement is right. Just that it doesn't. There may be different ways of.
I encode my to the source.
Mhm.
Will be different based on my problem statement, what I'm looking for.
Sure. That's the underlying thing. You encode them differently. So yeah, maybe that's a good way of saying that. Although we think more in terms of the architecture that generated latent space rather than thinking about the latency. Right. Yeah. So and crafting that architecture requires a lot of cleverness or trickery. Yeah. Yes, we'll discuss the decoder in full detail very soon. So so this was one. This is a segmentation problem. You take an image and you try to figure out where the cars are, where the trees are. So this is a translation of image and this architecture. So a lot of these approaches are popular now. The segmentation task is particularly important for the medical domain, where you want to look at, for example, the eye or lungs or or the brain and the scans of them and figure out these areas of interest. And the same encoder decoder architectures in a slide, which looks slightly different from the text ones, are used there also. Okay, and so coming to so this is one figure, the Google auto reply feature. So this again an encoder decoder architecture. Is the incoming mail, are you free tomorrow? That this is an LSTM. There are some internals which you can see here, and that gets compressed into this latent representation. And from that, you don't generate the same sentence. You generate a sort of translation of it, which is yes, what's up. Okay, and again, LSTM is responsible for generating it.
Where is supervised learning? You kind of previously kind of do some learning, and then you, based on that, you make the response.
So I haven't talked. So my starting point was these are these boxes with holes. You have to fill those holes. Only if you fill the holes right, you'll be able to generate the right sentence. Otherwise, you won't. Okay. Yeah. So I'm coming to that. So how do you fill the holes? I just want you to think about it for a moment. And there are holes all over. These W's are all over the place. And so the first principle is examples. Input and output, just the interface. You provide huge number of examples. Okay. And plus, that's not supervision comes with examples and the diffs or the loss function. So every time you compute something, you have to compare it with what you want, expect. And if there's an error, that error is extremely important. That is what helps you tune those holes. Okay, so program with examples and holes. And that's the principle behind the whole field across domains. Okay, so now we are coming to the machine translation business. Yeah. Sure. Mm-hmm.
How is that different? Is it another way of seeing? How is it different from a STM? Same thing, right?
The components are the same. There's a LSTM. There's a while loop working here, and a while loop that generates the sentence. And but these while loops do different things. Here, the while loop is responsible for compressing this sentence into an embedding later. Yeah, you can, call it predicting the output, inference, whatever you want to call it. Yes. So is your question that the LSTM is used both in the sort of encoding and the inference part?
How is it different? The LSTM. Yes, we have reverse it should be a different kind of function. So you have also the input is this one and the output is a yes.
So maybe we need to carefully look at here. The input is RU, and well, at a high level, this is the input and this is the output. Okay, that's a very high level. But then you decompose the task. Okay, so you decompose into the encoder part and the decoder part. What does the encoder do? It takes these word representation and computes this small thing, and the decoder takes this as the initializer state and does something different. It tries to predict the next word. Okay, so first word it takes just start symbol, just yes. Then it takes the word yes as input and tries to predict. Okay, so the way it works is different. So using the yes information of yes and this compressed representation from the past, it is able to generate words. Yes, the supervision is input and output. That's it. That's it. The rest of the internals is in the hand of the designer. Learning, learning. There are holes here. There are holes here. Yeah.
We have the same input and same output.
You want to generate it.
And there is narrowing down of the layers. Then it expands back in. So in encoder decoder, do we still have the same network? Just that the input and output are different?
The encoder and the decoder are different. Yeah.
expected output is not seen there.
Yes, that's right.
It's not like we are training half of the network separately and
No, we trend end to end because we are limited by the supervision we have. If you can give me better supervision, you can tell me what the thought vector for the sentence is, I'll be able to split this task.
maybe like we do autoencoder for the left side of which is the input and autoencoder for output and split these network into half and seven and something like that.
Sure. So you can compute latent representations for the language itself in predicting next word business and then use it as a representation both here and here. Okay, so that is what is done in the newer architecture. Yeah. So the essential idea is that you have to capture the meaning of the sentence in these small vectors. And if you have captured it good enough, you can use it everywhere.
What I understood is like we have character encoding, then we have word encoding, then we have thought.
Sentence embedding. Yeah. Yeah. You're just.
Then we, then we have a reply or whatever is changed on the thought bit. Or word encoding, sentence encoding.
So I am not able to catch your stream of thought. It's.
No, all are different problems. He has taken that sequence to explain us that first the character embedding, word embedding, and sentence embedding.
Yeah. Yeah. So all of that feeds in here. Yeah. Here, how do you convert from strings to vectors is a problem to be solved in many. You start from characters, word, blah blah blah. Once you get those vectors, then you have to encode the meaning of the sentence somehow. This is one particular way to do it. In this case, this is what is supposedly capturing the meaning of the sentence. And then using this meaning, I'm going to generate. Then you have to encode the meaning of the sentence. Who said? Okay. So what was the question?
So, like, for example, if you have 4 states that shown like character.
Yes. So that is here.
Yeah, that's all happened. Like,
Yeah.
What I understood is like similar to like word encoding, thought encoding, like sentence encoding is an layer.
Yes, you can think. Yeah, and I'm instead of representing it here, I'm representing it here.
So after sentence encoding, we can use it even for translation or for example chat code.
Yeah, that's why that's the generality of it, and there is a representation of the sentence, and you can use it in many different ways. You can use it to predict the next sentence that would have followed in this email also. It's very powerful representation, and I'm going to surprise you again by saying that this is not a good enough representation for the sentence, and we'll need to improve on it. But that's what the translation. So we'll be working with this encoder decoder architecture for translation. Yeah, you could think of instead of this reply, I generate the sentence in German, English sentence. Same overall architecture. The internals will see.
The way it's programmed, like when you put audio free tomorrow, so only output will get us, right? You can get like
Right.
probability, like MS WhatsApp, I guess today or something afternoon.
Yes, you can get a huge number of outputs. I'm thinking of the quickest way to. So here, what you say yes is actually a list of values. Okay, you have the whole vocabulary actually here. All the words that you could generate here and weights on it. Okay, and then you pick the one with highest weight, it turns out to be yes. So maybe the architecture part, how is being, sorry, what is the question? Yeah, so now you get it on LinkedIn also. You get a message and there's a short reply, and okay, good, sounds good. And that's automatically generated. Yes, but you can have a list of auto replies. What if you get a new one, which first you have to build that list of replies that may not be suited to some mail that you get. So there could be new ones that don't fall in the list. So this system generates the new sentence on its own, a grammatically correct sentence on its own. Is that clear?
Has this whole, all of our data. So basically, they are doing that mapping it. We are writing the answers for them. So they are finding the best answers for. They are just ranking our answers.
Right.
That's what they-
Yeah, so we supervise, so one way of explaining, we supervise Gmail's reply neural network by replying to these mails, and there are millions of people who have supervised it.
What I wonder is how, should I give all the details how to reply, or like, if you have a C3P or others, so it just knows everything, just a human being.
Right.
How
So,
it's just
so the yeah.
email, you give input and output all programmed.
Uh-huh.
Sometimes you have random output also. So obviously day to day it can also reply hard or cold by randomly. So how independent is that output?
Yeah, so the principles behind it is statistics. It has seen lots of sentences. It has seen that this sentence is accompanied with this one in most cases, in majority cases, or they are top two candidates. And that is what it has learned through looking at so much data. And to learn it in a principled way, this is the architecture. This is the helpful machinery but that's the basic. So now your question has many aspects to it, how intelligent it is in a way. So you could, on one side is just statistics. The data that it has seen, it will only generate stuff that is similar to that data.
Everything is an assistant. You see, assistant, you tell the assistant that, so I'm the boss, and tell them that I'm going home. So tells the enemy comes to tell some answer and tell them.
Right.
Plus, you can pick anything you want. So something like that. It can also.
So the assistant.
It's a sentence. Many.
Yeah. So the assistant task is FAQ. Banks side have standard questions, standard replies. A human being, to avoid a human effort in doing that, one could use this kind of machinery to. But FAQ is a very restricted domain, and the answers are sort of fixed for a given question. The problem is that once a user says the question, what does it map to in my database of questions? That's a tricky part. Again, these network examples will help you figure that out also. Okay. Essentially, human beings have done a lot of labor creating data, and now machineries can learn from it for specific tasks. And this is not magic. It takes huge amount of effort to do this correctly and nicely at the level of Google. But that's why they are Google.
I want to see like yes, no, thank you, something like that.
Other word of replies are also there. So it depends on the context of the data.
Are we on time or what is it?
Imagine that same sentence was are you
I can have a break. Achha, I'll
So now that is
just
confused and it hasn't that many examples of someone asking in a way that would it will be confused. Will give some weird answer. Instead of are you free tomorrow? If you ask are you dying tomorrow in the same sentence, it hasn't accounted those sentences in that purpose. So it might give some weird answer to that.
yeah. So if it so it generates data which is very similar, but again another effort behind these things is to make it slightly general. Okay, so we can have a quick break and come back and what are people? Yeah, go ahead with it.
For example, Google Chat.
Chat.
For Alexa, for example, just take Alexa. We ask a question so that it is calculated and it is everything. But it also needs some other information. For example, if I ask, if I can,
sorry?
if I can, I'm free like, for example, 12, something like that I'm asking for Alexa. So that to be able to first understand the sentences. So that's like thought and body thinking. So then it also needs
Context.
Context.
Yeah, so context is the general or the associated information beside the immediate text that is given by the user. The context. It could be his current book, it could be where he's sitting, it could be who has talked to recently.
To use both context and this thought, everybody then to use this.
And to model the context again nicely as vector is another art.
So most of these papers and articles, programs, I used to see this translation and stuff like that. But I never really seen like open source code use this, for example, translation plus some word and word like context and then give you.
Yeah, so if you look at dialogue generation, yeah, that under that subtopic you'll find resources like those. Yes, open source. And the dialogue generation is a very hot area of research. It has been for some time, particularly for these chatbots to sound intelligent.
So like basic things that we can form, maybe like using like calendars and stuff like that.
So
Open source.
I don't know of a particular reference of when people generally try to, for example, movie dialogue. They learn from the dialect text, the screenplay of movies, and try to generate similar conversations. That's I think where the thing started off. But particular kind of taking any. I don't know how. There are several I know, but I don't know a particular reference which applies it. It's open source and applies it to a particular.
Most of the TensorFlow examples that we see this like language translation.
Yes,
At least you can get.
so I mean, these are built like learning the language of programming, for example. So,
But along with context thing, like
and yeah,
something like chatbot, you need some other learning also should happen.
might need to search a bit more. Hello. Yeah. Is there a way to bring the volume of this from your speakers? Otherwise, I just turn it down and then. Yeah. So we start with machine translation. And again, let's see how much justice I can do within the next hour. It's a very broad topic, and yeah, so this chart is just introductory. It tells you that you might have seen for image classification or earlier the percentages were, maybe even lesser, like 50, 60s, and then they went up to 80 or something across a few years. So many of these problems which involve text, speech, or images have similar curves when deep learning based approaches were applied to them. You could get much better performance results as compared to the earlier where people used to write these rules by hand. Okay, so the machine translation, the most popular statistical machine translation, even though neural machine translation is also statistical, but the in the rule-based world, the approach was already called statistical machine translation, and there are a number of approaches which looked at phrases in the sentences to translate, or words, or syntax trees to translate. So, but this basically graph shows that the syntax based was growing, phrase based was growing this way, but neural methods were introduced 2015 2014 papers, and they suddenly took over, and it's 30 and 40 range. There's a particular metric that we'll talk about, but yeah, so that gives huge motivation for studying these methods and applying them to translation. Okay, so formal modeling, probability of the target sentence giving source in one language, target in another. And again, we're talking about probability because there could be multiple target sentences. You think of all the sentences in the target language as a set, and you want to assign weights to them and pick the best one, the highest weight. Okay, and so this is English to French, and it is useful to look at some examples to figure out if you had to write rules, how would you go about it? So roughly, you see that roughly the words correspond to words. The reason that these languages have similar languages are similar in some sense. So the maps to le program has been, there's something strange here, implemented, goes down to 3 words. Okay, so the first thing that you have lost is equilength. The input and output may not be similar. Output can in fact be smaller or bigger than. Okay, and the other thing that you have to learn is correspondence between word, input word, and output word. So here one input word corresponds to multiple output words. So you might have to learn functions like that also. Okay, some more example. This is, and it gets more complicated. That was, I think, one of the simpler examples. So now I can't pronounce French. Le prix de Nobel de paix. This is the input sentence, French. You want to convert into to receive the Nobel Prize. Okay. And this is sort of alignment setup. Okay, what happens? This and to one-to-one matching, they are both in the beginning of the sentence. Again, these two words have mapping, le and the. Something strange happens here. Now, if you had to convert this phrase, Prix Nobel de la Paix, to Nobel Peace Prize, what would you do? What are the operations that you need to do? So that's the problem, right? This sentence. So pre, if you look at the word pre, that has prize. That's what it means. So prize at the end of this sentence, pre is the beginning. So till now you will be just going left to right and mapping everything But now that is the problem. You have to ignore pre till you have covered these. Okay. Yes. Yeah. So you have to. Yes, bidirectional. Again, bidirectional is at a lower level. At a higher level, what? Forget about neural networks. If you had to write a while loop to do this. Sure, you're again going down a little bit deeper. So, sure. So that is again, there's a reordering involved here. That's what I was trying to get. And you have to decide when you're going left to, suppose you're just going left to right, you have to decide when to reorder. That this, or other way to look at it is when you come to this point, you have to pick which word I'll translate next. And it won't be the next one, it would be noble. And when you're here, you pick this one and this one and this one. When you're done here, then you go back and pick this one. Sure. Yeah. The underlying problem or the catch is that the word orderings in these two languages don't exactly match. So you can't just simply align them. Alignment is the, and you have to. Okay, some more examples. Did you have lunch? This is I just cut paste from Google, and I can't read Kannada, Malayalam, I can read Hindi. So now you can pick your language and try to do the same. You'll see that. So here the word ordering problem is. So this is a noun, and this is sort of adjective, or there are better ways, better forms of that you can. So it's roughly adjectives, and so it's a noun adjective reordering problem here between English. Here you have kya maps to did. You have. So you maps to aapne, aap and ne. There are other issues there. Have lunch. Have lunch. Reordering. So the problem with English versus most Indian languages is the subject, verb, object. English has subject, verb, object. Hindi has subject, object, verb. Okay. And right. So I think I understand, but there is a problem with the encoder sentence embedding thing that I'll just next slide will come to it. If that could be done, then if that embedding captured all the information about ordering and everything, that would be great. But that's where the problem, it doesn't capture it. And maybe you can test in your own language if it is one of them, or the SVO problem, subject, verb, or object problem is ubiquitous across. Yeah. So this is just to give intuition of what the. So we'll be using encoder decoder here, and what the encoder decoder has to struggle with in doing this translation. Okay, this is talk about decomposition. You can ignore this, but so those who can understand it, T is the target, S is the source, and given the source, you want to guess an alignment. Alignment is what I showed here. Okay, this thing is aligned to this. So phrases are aligned, not just words. Aligned phrases. You have to pick phrases and pick phrases to align, and pick the target and the alignment with the highest probability, and that's your. Okay, and how do you do that? It's basically you look at the source and target. I mean, essentially what that diagram. You try to compute features for pairs of things. You try to match this with this and see how much probable is that. You might try to match this with this here, and you end up saying that these few phrases have the highest probability. Okay, these are again rule based. If you had to do it manually, what is called the statistical machine translation. This is the old approach, which I mean, that's how it used to get done, and still there are these. Till recently, these rule-based approaches were the most popular ones. And how did we go? this is, I think, Spanish and English. And to convert this Spanish to English, we started off with a aligned phrase dictionary. This is computed from, say, Wikipedia. So Wikipedia has language, like the whole data is in more than 300 languages, or maybe even more. So if you have a English Wikipedia text on Donald Trump, there is a Tamil, Telugu, Hindi, and so many languages also. So there is a one-to-one correspondence between sort of each sentence. That's a huge, what is called a parallel corpus that can allow us to learn. So you take such a corpus and then try to look at phrases. Try to look at phrases and see which of them generally occur in two sentences which with high frequency. And you compute such pairs and with probabilities, how probable these are. And when you try to this is called a phrase table, and when you so and then I mean, this is the decomposition of the problem. I'll just tell you what is written intuitively. So you start left to right. You try to pick a phrase here and a phrase here. Is just a word here, which has a high probability existence in my table, previously existing table. So this table is my sort of oracle. Okay, so in this case, V and null is a pair. Okay, we are done here. Again, in this case, you do. Okay, so essentially, you try to split the sentence in parts so that the lookup in the table is high. And if you go all this far, you realize that for this pair, there's what is matching has less probability than this one. You just stop here. So roughly, and there's more. Okay, there's more stuff there, but let's skip that. Okay, so did I? So there's this metric called blue, and so I'm before jumping to how we. So I talk about the phrase table based translation approach. We'll talk about the neural way of doing it. But suppose you have a system that translates. You have to monitor how you have to have a metric on how good it is performing. So if you have given this sentence, this reference, and the automated system is outputting this, you want to give a quantifiable number, a score to this translation. And when you average it over the whole set, you will sort of know how good your translation, a metric for your translations. Okay, and blue score is the popular score, which now the thing about so if you were converting images, classifying images to cat, dog, whatever, it's pretty clear to most of the human beings unambiguously what is it. But here with sentences, there are multiple. So if the machine produced, there is a cat on the mat. Okay, suppose this was the reference and this is what machine produced, you would still be okay. I mean, this is the right translation, even though it's not an exact match, still a right translation. So that makes the problem of checking harder. Okay, and so there is a scoring system. Essentially, you instead of matching word by word, so this is a bad translation and weaker translation system. Instead of matching word by, you try to find small phrases or bigrams and try to see how many times the phrases occur here and how many times they occur in the reference. Okay, and you try to take a ratio of that. Okay, so that the cat occurs 2 times here, cat on the mat, this thing. So this is a sort of valid phrase which happens here once. Cat the never, it's not a valid English phrase in most cases. So cat the doesn't occur in my reference, 0. So I have generated a number of things. So all of these are ones. I have generated these twice where I would have expected just one, and this is generated once, whereas it shouldn't have been there. So this sort of tells you and you sum this up and sum this up. This is 4 and this is 6. Okay. Yeah. So so the difference sort of tells you that all the phrases were not, either they were over generated or they were lost. Okay, and this metric is, people are not very happy with this metric, but still this is the one that comes pretty close to human judgment, so people use it. And Jeremy Howard, if you know, doesn't like to discuss this metric because it's a things are awful, but Andrew likes to discuss this, so I got the slides. Okay, sorry. So you get a percentage score. It will be always between 0 and 1, or yeah, and you want higher. So a perfect match, suppose you try to match this with this, whatever n-gram you find here, whatever phrase you find here, you'll find it in the target sentence also, and exactly the same number of times. That's where it's the boundary is all set, and you want to maximize it. And typically the percentages are in 30s and 40s for good machine learning translation. So that's the two. Normally we work at 80 and 90s for image, but the reasons being that exact match is difficult, so you have this approximate heuristic to match it. Plus the machine learning translation system for longer sentences, generally most of the popular ones don't perform that, and even the Google one user on the So that was the curve I showed in the beginning. Yeah, so it's around 30 and 40 for the best ones. Yes. Okay, so that's a rough idea. You find phrases here and do a rough matching, not exact. And that's a metric once your translation system. This is not what is used to train the translation system. Translation system works by matching word one by one. I mean the training objective of the there's an expansion to it. Bilingual something understudy. It has a meaning why it's supposed to be an understudy of the human being who's doing the actual testing. So there are a number of metrics like that. This is one of the most popular. Yeah, and that was the basic one, and there's some penalty for if you're trying to generate 2 short sentences, there's a penalty to make it bigger. Anyway, so yeah, without blue you can't measure how good the system is. That's why it's essential to know. Okay, so we are back in the neural world. Okay, so I think it's a 2014 paper, sequence to sequence learning, and this should not be unfamiliar to you at this point. He loved to eat, captured into a sentence embedding, and then that embedding generates the sentence. Okay, again, if you go step by step, you take this word, embed it into a vector, encode. Is the LSTM or RNN working here? It combines meaning here. Okay, once you get this compressed meaning of the English sentence, you try to generate this, I think, German sentence. Yeah. And the way you do it is you put in a start symbol. Okay, and this generate the first word. Okay, how you are able, because this now that's why I talked about this phrase alignment. This thing has to do the phrase alignment inside. Okay, so that's the catch. In the yes, the whole machinery has to, the encoder has to help the decoder to do the alignment in some way. And now so R should be aligned with he. So S has some information corresponds to all those 4 words. Okay, very abstractly. Now to generate the first word, this should know that it should use the information related to he and generate R. Now once it has generated R, it takes in the same generated thing as input. If you know about language modeling, this should be pretty standard. Okay, once you take R and you get the compressed representation, you should be able to generate this. This corresponds to loved. Okay, so the machinery has to somehow focus on the part of S based on the previous word generated and and the current S and the initial S, partial S. Right. So at every step, again, I'll go back to the while loop sum. Sum is transformed at every step. S or H is transformed at every step, from here to here and from here to here. Okay. This is sort of initial biasing of the network with that knowledge. So again, the hidden is the input, not the layer. So there is input and there's a transformer. So input is this. After transforming, you get an embedding. Transform, you get an output here, which is the embedding. Transform. Yes. No, the S is also transformed here. So yeah, so it's probably necessary to go into how, but again, I tried to avoid getting into the internals of S, but F H T minus 1 X H T. If you remember just this, S is being fed here. X is air. Okay. And there's this internal holes and transformation which give you HT. HT is not shown here, it is here. And it also, there is another, call it G, which takes maybe HT minus 1 and X and gives you. So for the encoder, that is X. For the decoder, it's the word in the target language. Okay, so they are both RNNs. They both have those same equation, but what they have different tasks. This guy has to compress the sentence or encode it. This guy has to generate new words. Okay, so their machinery is. Does that clarify your question? Or? No, it S.
The transformation only happens here. Does it happen here also?
So what goes here is HT. So S is this. It's transformed to HT. At every step, it's like the sum plus I happens at every step. Okay, so so intuitively, it also takes into account what was inputted earlier at every step. Here, S knows that all this was input, besides the fact that the input translation. Okay, and we were next slide going to break this single S into several parts, so that will be more clear. But that's the okay. And again, there are more details here. The output is not a single thing; it's actually a branch over all the vocabulary, and the word has the highest probability. And what is called the soft max layer essentially enables you to normalize among them, and then you pick the highest probable thing. Okay, so doing this, if you have a 80,000 word vocabulary, this thing needs to be done very efficiently, and there are many tricks to handle large vocabulary. There are steps, yeah. Yes, so RNN cell is just this. That's why, and you have to repeat it. Yeah, but there are again variations. You can have stacks of these cells which could be different from each other. And so the hidden state typically is 512 1,000 real numbers. You can calculate your memory based on that. Yeah, and but it's not just the 1,000. There is generally much more complicated inside it. So it has to. So one way for it to know is to look at this dot, and so it has to generate the end of the sentence. So and it also, when you're feeding in data, it also learns to recognize when the sentence ends. That's part of the learning.
For example, decoder part, you see like second word,
Leaped, yeah.
So it's like in probability terms, if you play probability of y to give yes, and y1.
Yes. Yes. We have to be more careful with the decomposition here, but please go ahead. Yeah.
Very rough idea.
Yes. Yeah.
The encode thing, that should be only a function of, for example, English language, or you could like also have the learning when you try to do the training.
Yeah. So what it learns here, the meaning of
Learns the encoder or LSTM.
yes. So maybe if I try to answer the meaning of, it has to capture the meaning. And loved her versus loved to eat are two different things. So it should learn enough stuff by combining these two word vectors to distinguish whether it's loved to eat or loved her. Not clear? The context, yes. So it has the responsibility of, it has to learn the context of, so each word may have some meaning in its own, but when it occurs in this particular sentence context, it can assume a slightly different meaning. Okay? Hmm.
Find the NLP network, like encoder and decoder. Once we have Latin, for example, we train it using like English and German conversations. Then we can keep the encoder of the same language, and we can replace it with some Tamil
Right.
decoder.
Right.
So if it's going to work, then it means that encoder learning happens somewhat like different of whatever is there in the decoder.
Yes.
When you do the training.
Yes, so that is multilingual translation, and I mean you try to use the same network to do multiple languages. Yes. Normally you will, we will come to it, but the short answer is that if you have to use the same thing to encode multiple languages, you have to have similar representations for the words that are going in the vectors. So these words, although mean different things to us because we know different languages, when you map them to vector spaces, you can do it in a way that all of them similar meaning stuff in different languages are a cluster. Okay, and that will help you use the same machine. But that's where a lot of research recently has been done, and it's sort of cutting edge, right? How to do that efficiently. Yeah. So this is the output. No, it is the just this sentence, this sentence. Ye- Yeah, so maybe you should. What is the question? If you think of this network as the black box, what do you give at sort of every step? Yes. 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 Right. So there are many questions in there. Suppose first of all you have a pair of sentences that you have, that is your starting point. The lengths might be different. One simple way, just fix a max length, add some padding, max length. Okay, then you just encode this, the whole thing, get a vector, and when you start generating output, you just give this the output sentence. You don't worry about aligning it. Expect the network to align it. Yes. So maybe if I draw this diagram, this is my sentence, English sentence. Okay, just call it a. Suppose this is just one word, and I get a D y hat is a predicted output, and I know the corresponding y for this word. So you can, if you want an arrow like this is also there, Okay. And when I get this, I compute the diff. Okay.
These are going to be embedding vectors. We want the direction of
So the output here is actually the word. So the network converts. So at this softmax layer, the you have yes, and then you pick the best one.
how will we find the diff towards
Then you pick the best one, highest probability. That's an index that corresponds to some word in your vocabulary. Now you've gotten word. Now you have a word that is predicted. You also know what is the next word you want to be predicted. Compute the diff. Yeah, and it's not exactly. I mean, there is a more mathematical way of doing exactly this. Sure. In general, the context is very important. Yeah. So let's go ahead and maybe things will be more clear with, because we are going to change the. Uh, how to do multilingual translation? There are several ways, but we'll get to it. So if this is the diagram that makes you makes it clearer, this is a sentence, word vectors corresponding to it. Actually, so now this is complicated, and there are a number of layers that process the word vectors. You get the encoder, and this what you get here is S, is a concatenation of this. You feed it into the recorder, this thing, that becomes this thing. I'm not sure it's the same or not. You feed in the first word, which is EU, and it should be beginning. Which should be beginning of string, I think. Yeah, beginning of string. You get one output word. That word is fed in here. That generates the next output. When you get this output word, you have a sentence here. You just match the first word with the first. Match the second word with the second. So you force the network to generate the right sequence of words and the right words. And if it's not, you flag an error. So it goes, so the way the machinery is set up. So we haven't talked about how it learns the weights and all that. There's an algorithm called backpropagation. And essentially, we have set up a series of transformations, get the output, get the loss. There's a way to propagate it back in a very mathematical way to every weight and change it. Okay, and that's what the backpropagation gradient-based learning does. We'll have to.
I think the expression here is probability of the should be high, so the network would give some probability to the and that difference is then backpropagated.
That's right. That's the error, and error is backpropagated. Yeah, and if you're guessing something. Yeah. So there are quite a few moving parts here. I mean, you don't generally, it's not advisable to look at this complicated and think about backpropagation. You should maybe start with the simple feed-forward network, and actually you can just write all the backpropagation rules. So again, there is more detail in the output. There's you since you are generating several things, it's like this is the word the, this is the word blah blah. You're generating several things in one go. You can sort of think of multiple possibilities. You can pick the first one here, second one here, third one here, fourth one here, or you can fourth, third. So essentially, you can, this structure or this setup allows you to generate multiple different strings. And how do you pick the best ones? You just compute their combined probability. So if this path has higher probability than this path, then you pick this one. Okay, and you can pick K or N top. And that's why the beam has n top. So, or based on the number of n you want. So you can just, whatever, there are 4 cross 4 strings here. you pick the ones with the k ones with highest probability. And again, this beam search is a very old. I mean, it has roots in HMM and what should I call it? More structured space search, and it can get, this algorithm is also pretty complicated, and there are many variations possible to, depending on what you want to generate or how diverse you want to be. Right. So context, if I just say context, so if I probably some examples will make it clear, but if I hadn't generated I, instead of that I generated V, the first step, my verb will change at a later point. I have versus V, okay, you. Yeah, so the next words, although I will, you have, I have, we have, give me some, she has, okay, she has, but he has also. So if, so he has is in some way similar to I have, okay, but so, but if I generated I should generate that right, and so that's why this context is important for them. And that's just a very simple example. There are a number of cases there. So yeah, and I'm going to break the single thought vector model with this slide. So now these are all diagrams which look similar, and I'm trying to do a variation based learning on the audience so that you get to get the meat of it and not stuck on the. So the input, embedding, I talked about by LSTMs earlier, right? In general, the first. So these diagrams, I'll actually get to the Google NMT, Google Neural Machine Translation Engine. That was, so I talked about phrase-based translation. What you see on Google Translate till 2016 September was phrase-based translation. It was working pretty good, but so this research happened in the span of, I think, 1 or 2 years, and it was so successful, and it outperformed phrase-based translation, and Google put into production this variation of this engine with several optimization in 2016. The whole Google Translate was sort of swapped with this completely new world thing. So just yeah, it was both in terms of how quick research reached production as well as the amount of performance gain that happened that convinced the whole organization to make the switch. Okay, so maybe, okay, the key, we are trying to, till now, we are trying to capture the meaning of the sentence in a single vector, which is, I mean, pretty stupid thing to do, okay? Because there are a number of reasons there. One is that this transformation of the last word happened much closer to this generation of vector as compared to this. So you would sort of intuitively expect this information might be more lost than this one. Even if you do backward, the middle information might be lost. All sorts. So even though we want to compress the information into vectors, it turned out, or people realized, that having a single vector is not good enough. We should just have one vector per word. So we still have the encoding process where the initial word embeddings sort of, they are juggled together, and you compute the final embeddings or final representations of each word. So there are 4 here, 5 here, and 5 here. Okay, but now instead of a single state S, you have this split encoding of the sentence, and this solves that. So I was talking about, at this point, when you see null, you should now aligning things become more intuitive. Okay, so when you see null, this is the beginning of the sentence, you sort of, the machine can normally can automatically try focusing on the first word. Okay, and if it is successful, the word at this point, it can, now since it has these 5 representations for these words, it can see that the word is closest to this one. Okay. And so maybe the next candidate is the word loved. So maybe I should try to translate loved. Okay, that's trying to give a rough intuition of why this splitting is. So the problem, so it's always good to think of it in a rule-based way. We had to map phrases to phrases, and the architecture, the previous architecture, was sort of doing it magically. There was we hadn't architected it good enough to do the alignment explicitly. Whereas this, if you split it, then there is a way to align what you generate with words here more explicitly. And that is called attention. Okay, so attention, well, although we have come to that concept in this particular fashion, it's a pretty generic concept, although this paper brought it to the front. So whenever we look at an image, or we focus on some parts of it, we don't focus on and that's how we recognize whether there's a cat or a dog. The network should also have the ability to do that. If it does that, it will be more performant, it will be more effective. That's sort of capturing our intuition into network. Now the previous architecture didn't. By adding attention, and I'll tell you how exactly, we are able to focus onto different words in this first sentence to translate. Yes, it's there's a dot product going on there. Dot product has the plus inside, so it's all will boil down to dot products everywhere. So wi plus wixi sum. Yeah, and there are w's here and there are x's here, and which one to weight more is the attention weight, in simple words. Yeah, we'll get there. Yes. Yeah. So the starting word is always fixed. It's the start of the string, or beginning of string, and then you are whatever comes out as the output is passed in. So the responsibility of the network is to get the. So initially it gets awfully wrong, and then so you have to train a huge amount of data, and after some time the holes get filled in such a way that you start getting the right words or the nearby words. That's how the. So vocabulary as such is fixed. A huge, you take 40,000, 80,000 for the real ones, and you assign numbers to it. So you have integer IDs for each of those words, and what you generate here is one integer ID, which is the highest, and that's converted. Okay. So the matching happens. You take 10, convert it into the word vector. You also have vector here. So we are jumping ahead, but I hope audience is coming along. So you from you have to, looking at this word, you have to learn to focus on loved. Okay, so you take the embedding of this, which is a vector, and you match it with the encoded versions here. Yeah, and then you figure out that it's closest to this one, and there's some logic which tells you to focus on the next one. Yeah, so the matching, that's why boiling everything down to the vector space helps you just do the dot product and do the matching. So dot product and weighted sum, that's all that is going on. Can you I just I'll illustrate the same thing. I am a student, okay, and this is encoded into vectors here, and then when I'm at the first position, this beginning of sentence, this thing I feed this, or the encoded version of this. So I encode this part also, because this is just a string, and I have to convert into vector. I get a vector for the first decoder output and a set of vectors for the encoded. I match this vector with all of these. I find that this one has the highest weight. Okay, so that means that I have to translate I now. Okay, and there are a number of things going on. Maybe you should ask the question. Yeah. Yeah. Right. Right. So reordering means that it's very simple to model reordering. I am, suppose the next word, I want to focus on a student and not I. This attention mechanism will just have this highest weight, and that will pick up this. Okay, so the reordering is automatically captured with this attention. Yes. So at every step, you compute the attention weights, and there's minor thing. So how does the math work? Is these are not. So intuitively, you would think that you just pick one word. Why do you need to have weights on all of them? Okay, you just want to pick one word which we translate, but that breaks the continuous modeling or differentiability. So what you do is you have a whole, you score everything like you do with probabilities. You scroll everything, and the one that you want to most focus on gets the highest weight. Okay, and then if you have these encoders E1, E2, En, you have the weights W1, W2, Wn. These weights are 0.5, 0.3, and these are the encoder. You do a dot product, which is Wi, Ei, sum. Okay. So you sort of combine. So this is again a thought vector being computed at this point, which is a weighted thought vector where the weight of this thing is highest and the others are. So the machinery doesn't let you just focus on one word and just filter out other, but it indirectly, to keep this continuity of expressions, stay in the continuous domain of functions, you weight one of them higher, and the output that comes out, it's actually called the context vector now, and I think it makes sense intuitively. The context vector contains most from here and less from there. Okay, and that context vector is now used in the decoder along with the previous hidden state and the current. X, H, C. X is the input, or maybe here X, previous hidden state, and the context. They together get, and you compute the next output. Okay. Yeah, the context vector is a weighted thought vector from the source language, if that makes sense. Attention vector is also computed on the source. Which word in the source language you want to translate next? That's what it answers.
But that depends on, like, for example, SVO, target language is different.
Sure.
So that's the thing which affects the
So
attention weight.
yeah, so what the number of things that determine what they should, including the language, including what is the last word, including what has been translated. So everything that was affecting earlier, the hidden state, plus the similarity between this thing and the encoding. So the embedding of these two. Okay. So yeah, so again, attention is, again, the basic idea is just weighted sum or a dot product of you assign weights to the encoding. But the way it is used, and it gets more complicated. The way you get more complicated than a simple dot product to compute the attention. So it takes some time to fully absorb it. Yeah, I have a more step-by-step. I'm not sure. Yeah, so maybe just in formulas. You have the encoded sentences, E1 to En. You have the current decoder hidden state, DJ. Okay. You compute pairwise similarity scores. I call it similarity, compatibility, whatever you want to. That's a very vague notion of what happens there. Of DJ, the current decoder state, and all the encoder states. Okay, you get a vector that is pairwise length for yeah, or length of the number of sentence, encoded sentence. Then you normalize these scores. If you're familiar with SMART, it's a weighted, you try to bring it down in the range 0 to 1. Okay. And these are my attention weights that you're seeing 0.1, 0.3. And then you weight the encoders by these attention weights, you get the context. The context is used with the current decoder state to compute the next decoder state. Okay, so it's a quite a bit to absorb quickly, but I hope the intuition is coming across. Yeah, and generally, if you start writing these AJIs and number of indices increase, it's goes out of your head. If you can instead write in terms of vectors, take a E vector and do a vector softmax, and then it becomes cleaner to write these things. So since the introduction of attention in that paper for the task of translation, attention has spread out to almost every task that people want to solve. And so you want to classify, you want to focus onto a particular word, like the mobile example. So instead of just chucking along and computing the sum of the embeddings, you want to put more weight on the words that are more important and use them for classification. So it has gone to image or speech everywhere. This encoder decoder model with attention on the encoder outputs is just ubiquitous now. Okay, this is just, yeah, I mean, these are the encoded vectors. These are the attention weights. This one is the highest, and do a dot product and get there's a nice way to visualize things. So attention also gives you now interpretability into the system. Okay, what do you mean? So when you're looking at the thought vector encoder decoder where the symbols, you didn't know what was inside that state and how the translation worked. Now with this attention to every step, you can see, oh, this is the word I'm focusing on most. So if I'm focusing on the wrong word, it gives some insight into the modeler to correct. And this is the sort of confusion matrix is a general metric for the output, matching the outputs. This is attention. Huh? Attention matrix, yes. And it's very simple to read. I mean, if you stare at it, you'll just figure out what is going on. This is French, this is English. And S, she is matches with A here. Ans matches with 5. Sorry, 5 years. Huh? Yeah, so the color coding is so if this is white, it's near 1. And this is a very black and white model, so maybe it's not a good one. So these are the highest points of attention. So every word, when I'm trying to decode here, I have to choose between all these words to focus on. And so I have an attention vector like this, and this is the highest point. Yeah, which is white. So you just normally these diagrams are in color, so you get much better. So generally there are multiple words that are focused on. Okay, so if I have communicated the idea of attention to you, I'm not. Yeah, the material that I have will at least take a few more hours. So I'll go into a Rajdhani Express mode and just. So instead of the simple dot product mode, you could have more complicated functions which take the Q and K. Now I'll change from decoder state DJ to query and encoder state to key. So whatever you see in the encoder are the keys. Think of hash table now, okay? Are the keys, and output the decoder is the Q. So the query has to match with one of these and pick up its value. It makes sense. Okay. I think we will do something. Yeah. Thank you. So you have to compute a matching between Q and K, and you could design all sorts of complicated function to that. Yeah, query and key. I'm generalizing it from the encoder decoder states that we were talking about. I'm calling the decoder states the query, because this is what is my current state, and I'm querying into the encoder states and trying to figure out which is the one that I need to focus on. So I call those the keys. Okay, actually the keys and values are both the same there. But So you have to, now you can switch to this mental model. The query and key has to match and compute a new value. And across years, this is a more linear additive kind of model where you do additive combination of Q and K. This is where you multiply Q and K and try to figure out. So understanding these will take some time. But the simple dot product is always there. You do a simple dot product, you compute a score, that is the attention score. Okay, and there's a scale dot product also. So this is a snapshot of the Google NMT, which was actually deployed, and they wrote a paper nicely to explain many aspects of it. It has 8 encoder layers. So the complexity of, so initially you encode, this is the actual system, or probably very close to it. You take an input sentence, you encode it here, bunch of encoder layers. These 5 representation of vectors are the refined or more abstract representation of these 5. This is what we work with, the keys. Okay. Decoder again has these 8 layers, which I think they are only forward. Yeah. And it's very carefully designed, every part, why they have chosen that component, what are the inputs that feeding it, everything has been very carefully designed. And and so when you generate it, the basic mechanism is the same. When you generate the next thing, attend to one of those words, and that feeds in. Okay, why you need these 8 layers is essentially you want to capture the context of the sentence properly, the words occurring together, and these layers help you come up with better representation of the word, which will actually help. So you actually you want to both capture the context of the language as well as make it the target language friendly, so that when you match this, there is a similarity. And yes, yes. That again, this architecture is not different for different languages, but how should I? Yeah, I just said. Yeah. In general, we have multiple layers because the first layer can learn the matching between, say, he and loved. The next layer can love. The long-term dependencies are better captured at this layer. That is one of the reasons. Yeah. Yeah. And yeah. Yeah, I don't see convolution here, although there might be something. These are all recurrent layers. Yeah, but it won't be a surprise if, I mean, too different from, you could easily combine convolution with recurrence here. And sometimes this layer, Yeah, so I mean, so this is the paper which is not visible. Better between. So you can, one way to think about it is that it refines the embedding of each word by incorporating context from. And one of the issues is that all of the stuff happens inside by these geometric transformation W, X, and so interpreting them is very ad hoc. I mean, after doing lots of experiments, people come up with their own interpretations, and then everybody sticks by it. But I don't think anybody knows what is exactly going on there, which is one of the problems with, although these neural networks perform very well, if they don't perform well, or if you ask why it gave this output, it becomes hard to answer those questions. Softmax is just the normalized sum modified. W1 divided by W1 Wn. Okay, this is the, if you have W1 to Wn, yes, So this will put all the values between 0 and 1, and a small twist to it, exponent, that will raise the higher values even higher. You'll still get the thing between 0 and 1. Yeah, that's a popular, because of its normalization property and exponential, it's the popular layer at the end, where you have these 5 categories. You have the weights for these 5 categories, and you want to bring them between 0 and 1, and then pick one of them. Yes, it becomes the by doing the normalization, you get the probability. Is that? Yeah. No, it's not. Yeah. No, it is just the normalization operator. Okay. Yeah. So, I mean, the one property of this, so we'll get into the multilingual business, but yeah. So since they found that it was working so nicely for several languages, they threw more languages at it, and so now this diagram needs to be. So they had one set where they translated English to Japanese. They had another set where they translated Japanese to Korean. Okay, but there's some modification that you can do. Essentially, you can also add, besides the sentence, you can add the target identifier. You can say that if you want to transfer, you add FR here, okay, or Spanish. So that way you can now use this architecture for arbitrary pair of languages. Okay, but yes, personalized to the language, yes. And by doing that, they trained the same system. So now earlier we were stuck to pair of languages and the data there, and one network for each pair. Now this generalizes it. For several pairs, you have the same network, meaning the same weights, same holes. And so it gets to learn from so many examples. And now the advantage that, now if English to Japanese is working, now suppose you don't have English to Korean, but by transitivity, you can go from English to Japanese, feed it as an input Japanese, and go to Korean. Because you have trained these networks to capture Japanese Korean well and English Japanese well. Okay, so I mean their selling point was that we haven't seen we don't have Japanese Korean translation data, as much of it. We have very little. But because we had a lot of English Japanese and Japan, sorry, I am getting confused here. And English Japanese and Japanese Korean data, we were able to get a new kind of mapping which we hadn't seen before, and that performs not as well as having the original data, but relatively good. So yeah, so that is very cool in the sense that we can call it transfer learning, call it reusing all knowledge or multiple sources of knowledge into a single box. That thing is very useful for building general systems. Yes. Yeah, so it has to. Yeah, so the language identifier helps you attend to that identifier also in coming up with the next word. You can think of it. If it is a word ordering that it has to capture, it has to do it through this attention mechanism. Yes, so they have a single train network for all these languages. Oh. Okay.
So am I finding that some of these parameters are similar in just as in image processing, the earlier layers are lines and
So if you're asking what these layers represented, no.
earlier layers are similar for images.
Yes.
Earlier layers are similar.
Yes.
That's what they observed, and they could rate
Huh.
in the language modeling, if possible. Another is Japanese to Korean. Yes, so is it there? Is it are the earlier parameters similar here also?
I don't know, and I don't think I've seen something like they yeah. So I don't know. Interpreting these networks is harder over text than images. You can see stuff, and those kernels are somewhat similar to here. The other ways to interpret it, sometimes they figure out which word is giving more. Some of the neurons correspond to some types of words. There's some other interpret, but in this I haven't seen much interpreted except attention. You always know what you focus on, and that helps a lot. Okay. I'm not, I mean, there is stuff to cover, but I think so yeah, we have been talking about words, characters, something called byte pair encoding, where essentially you can have a fixed vocabulary, and then there'll always be, you move to a new domain, you'll have new words. And what do you do then? You start, saying that I don't know this word, I do this. That's what OOV output is, out of vocabulary. That's the output that if you don't recognize it. To avoid doing that, there are several tricks, but there's a more systematic way of representing words as combination of their parts, and that is very effective in these. It's again started from the translation architectures, and now it's everywhere. Wherever you want to handle newer words in a seamless way, so there is had some slides on the algorithm. And this is a 17 paper, which is, I think, has so we have made some assumptions. So earlier we were stuck on the thought vector. We got rid of that, and we have a split representation now with attention. Now we had another assumption of the recurrence, having a recurrent layer. There are problems with recurrence. Essentially, the sequential. You only compute the next thing after the previous thing is ready, and that stops parallelization. Okay, you could switch to CNNs, but then CNNs have the small window. You want to look back, long back. So there are tricks that you can play with CNNs and dilated CNNs that can help you. But yeah, so these guys, a lot of people wanted to get rid of RNNs, and they were trying to figure out a good architecture for it. And this transformer architecture, again from Google, and it's probably the state of the art architecture for machine translation tasks and for other tasks, is what they came up with to encode the sentence and do the transfer. Essentially, it doesn't have recurrent units. It has only, every word is, I'm not sure if you have, yeah. So every thinking machines are 2 words. You just encode this through a layer called self-attention. Okay, attention is again. So paper is called attention is all you need. Means that throw away recurrence, throw away anything else, and we can live with attention, and this paper actually outperformed all previous, including the Google NMT architecture on the translation task. So they invented this thing called self-attention. They didn't invent, there was previous, but they incorporated it. And so essentially what it does is incorporate the context. So RNN, you go left to right, you are incorporating context, and if you're too far, then start from right to left. And that's now in hindsight, it might seem like a very inefficient way of doing it. The self-attention essentially, tries to combine. You think of a data flow happening from, you have to compute this, combine this word and this word, and compute this. Compute this, combine this word and this word and this word and this word. A more parallel kind of, what's the, there has to be a more of a merge operator over all the words. Okay, and just every step merge. And by using the attention on what to merge in the next step, they get good representation. So this is the building block of that architecture, where you sort of merge the context, compute this representation, normalize, feed forward this. So data, except the transfer happening here, it just goes forward. And so for the rest of the sentence, you can also mostly go forward, except at this stage where you have to transfer information. So it reduces the, instead we were earlier going from left to right, step by step. And if you're there 10 layers, this layer computes and then the next layer works. And then it's extremely horribly non-parallel sequential architecture. So yeah. Yes, it uses all of them and uses them efficiently. There's essentially another dot product happening over these. Yeah. Right. But convolution has a fixed window. I think that is there. Yeah. So convolution has a fixed window. This guy goes anywhere. The drawback is that you know the exact weights associated with every guy. You know where the information came from. Whereas here you compute these weights dynamically through attention. And so these weights, you don't, after you sum them up, you don't know where they came from. So that causes some loss, and then there are ways to, yes, localization has been lost.
Looks like simple training.
Yes.
Don't have
Yes. So if you think that RNN are a dangerous beast or very hard to handle, which if you try to implement them or used to in the earlier versions of TensorFlow, you used to end up doing lots of small things to set up a cell. So this takes away a lot of pain, right? A lot of things, but RNNs now I have to go back and defend the RNNs, that this automatic merging that was happening, the context, that has to be sort of recreated in the self-attention layer here. Plus, you have to record the positions of. Okay, so so in RNN you automatically know that if you have run 4 steps, you have covered 4 elements, and you know the distance between 2 elements. Here, if you just run everything parallel, this word doesn't know how far it is from the other relevant word. So you have to incorporate that information also. And there's a thing called positional encoding, which does it. But anyway, I mean, it's good to just see some visuals. And so, yeah, maybe for the rest, for just to back up, I introduced attention from decoder to encoder. Okay, that was a cross attention you can go. This is self-attention by name. It's happening inside encoder, and it's happening inside decoder also. So what basically it's doing is, so this is one layer of the encoder, next layer of the encoder. Okay, the same words are getting encoded. You have embedding here, embedding here, embedding here. These are being, so if you look at the embedding of it here, these arrows tell you where it focuses on. Okay, so the animal didn't cross the street because it was too tired. It learns to focus on both it takes a while to interpret both the animal, this is dark animal, and tired. Okay, so when you had the initial embedding at the bottom layer, you had the words embedding for animal and cross and street, and because those were sort of independent embeddings. By doing this multiple merge operations, self-attention, what happens that it learns to understand that it actually refers to the animal here, and the embedding of it captures the information corresponding to animals and tired. So it captures sort of you can think of an average of, that's not fully correct, but the embedding of it will become an average of animals embedding and tired's embedding. And that's the way it captures it merges the semantic. Only this sentence, only this, yes. So at one time, you just see this input and output sentence. That's all you see. Going beyond that is a separate problem. There are other ways to look up knowledge bases and all. Yes, it is. Yeah, I mean, I'm not sure if I have the equation. Essentially, the idea is that you have the embedding for it here, call it the query. All other embeddings, call it the key. Match the query with the key. wherever you have the highest matching, highest weight. Okay, so if you do that matching across, you'll find that weights here and weights here. Maybe not in the initial layer. This is the layer 5 when it has learned some stuff to actually focus on the right thing. So it's just again keys and query matching. I don't know. Thank you. Okay, I am trying to just wrap up now. I think. Yeah. Yes. Yeah. So this is just, it's 18 and 17. So getting it productized, people understanding it properly, improving that is all going on. Yeah.
I understand self-admission and all the stuff. So accuracy, I'm not seeing any much improvement. Only thing is that performance-wise, sequences.
So both. So
understand this machine neural machine where is it going?
The short answer would be multilingual. Multilingual, trying to do it, not having a encoder decoder for every pair, but for having one universal encoder, one universal decoder. That's the sort of holy grail, and people are trying to get there. That's what. To get to that, you have to solve several sub problems, including performance, including getting data, and this is just static translation. You're given one. When you look at a corpus, when you have people involved who translate, there's a whole industry of people translating stuff. There are other problems that how do you fix these translation if they are slightly wrong? Because these systems will always be, at least now till now they are being. So how do you fix them very quickly, and providing user assistance to fix them through these networks? So we are just studying the core problem here. Bringing it to practice has n number of different variants of it. And
actually, I was understanding multi-layer sentence, multi-language. Something happening in that area, and I would say that I'm part of the
so under the multilingual umbrella, that is also essentially what I've told you. Convert the words into vectors. That's the starting point.
So, encoding numbers might come say I use simulation language. Encoding might match. This is the match.
Right.
Yeah, the source itself is a combination of multiple languages.
Sure.
So,
But
and I say I want to convert it. See, I very third person we only understand. I know partially English, partially Kannada. I mix and speak. And what you want is only English. I'm just trying to understand.
Sure.
So basically, it should be converted into one language called English. Is something happening in that?
So,
we achieve with this existing.
Do you think what I just explained can also solve the problem?
That's what I was trying to map. Actually,
so maybe just go back to the step-by-step architecture. The key part is getting from, if you have a sentence, you have to get in vector embedding of the sentence, and the sentence are different words. Different words have their own embeddings. You can just combine them.
Embeddings itself, I think.
You don't like him? No, not confused. You don't like them. That's a different thing.
It's not liking basically every language, every word will have its own embedding. So if I combine multiple languages, the embedding vectors might match the same word.
I think it depends on the corpus for which we are.
Yeah, the corpus is
so,
Yes.
if we have a corpus good enough for these multilingual sentences, we can come up with
today we may not have that kind of corpus. So because the corpus which are created to the best of my language are separate for every language. We try to combine all this stuff. Because I see it's a different problem. See, basically I am from outside Kannada, and I'm trying to learn Kannada, I'm trying to write certain things. I speak basically part of my language and part of Kannada, and you only understand Kannada. So I see it's a very good opportunity to kind of
That translation system could be.
Eventually, over a period of time, I may be good at Kannada. Till now, I part of Kannada and part of my native language I speak.
Yeah.
So
Just stressing on it, it would be extremely useful if we had translation systems that are as on our mobile phones very visible. So I'll again point you to the problems that you talked about, different vectors and different, those are the problems to be solved. But the approach remains the same. How do you get vectors which are multilingual and if the two vectors, two words across language have the same meaning, the vectors should be same. Yeah. So again.
If you see on Google keyboard, you swipe. So after a while, if you swipe in English also, it will predict the Hindi words. You keep on typing in that way. If you say "aap kaise ho," and if you swipe it like that, "aap A-A-P," it will give you "aap." So it is trying to learn itself.
mapping of word.
So I'm still say, did you get the?
Doing inference or doing the how it is how much completely
Resources and yes. So again, all these systems are, all these systems are tied to what are called GPUs, because you have to perform these several big dot products across matrices. The whole thing is just set up on blah blah blah, and to do them fast and on multiple sentences, you need to have specialized processing which GPUs provide. Right. So the effort right now, for example, there's a tool TensorFlow by Google, which out in 2015, and they have been trying to continuously improve it. The goal there is to compress the networks. Those big ones get compressed with minimal loss of accuracy, and they run on your mobile. That is where things are going. You can do that even right now for some very popular image networks, right? So the one that I showed, InceptionNet. So somehow there is a race, techniques in image processing with deep learning developed fast ahead of speech, and so there they are slightly ahead in compressing these networks with performance and getting them run both here and in a browser also. So browser, if you have a even simple GPU, browser has WebGL libraries and all that. So there is a huge amount of work across. So that's why viewing this whole programming by example paradigm as a software 2.0 is helpful, I think, because there's a whole stack like a network stack or whatever, from compiler level to application level being optimized by research and production as we speak. Yeah, and so it's a very within the next week you'll see at least one paper on that problem. I'm not going to write. There are people who are going. I'm just stressing on the way the things are processing. Progress is happening. Yeah. So, and yeah. So this is one of the, there are English to German, English to French tasks, and it's sort of the leaderboard on. So before that, yeah, now it's all attention you need. That's the transformer network without the RN is the leader. Yes. So the field of machine translation is 1980s, where IBM had huge. There are several IBM models, the SMT. So the data preparation that was also is there. So the most popular and biggest, these are million lines of parallel. Million lines. So many languages have huge corpus, and the problem is just to absorb that into a network, which is for this. Other languages, English, Hindi, for example, there is still a decent corpus. But if you go to more, less spoken languages, there's lesser data, and you want to conquer that domain also. So effort is data collection is one of the key problems. So the statistical machine translation, the one that I showed you in May, you have these phrase tables. You build these phrase tables, right? And then you have an algorithm which goes left to right and tries to predict the next phrase to map to. And those algorithms are also pretty good. These algorithms outperform them, but they remain, till few years back, they were the state of the art. And still there are optimization done there which have to be learned from. People are trying to improve these. Okay, so I think that should, yeah, we didn't go too deep into the transformer, but self-attention is this thing called multi-head attention. And so it gets, yeah, it's all dot product sets of them. What do you attend to? You have to be, yeah, and that's how you model the network to set that up is the. Hmm.
Image processing based neural networks and language processing.
Hmm.
So for image processing, you see like small companies can work on it. This is like each image processing algorithm detection object anything is on different field, like they have to develop some specialized network. So they have some research companies can do their own specialized work.
Variants of the network.
But when it comes to natural language processing, it's very big one to enter in. Second thing is
It's a big, sorry?
Big one is like we need a lot of corpuses, like data.
Which is true for image also and speech also. It's not different at all.
The thing is, Google is going to develop neural vision translation. It's going to be the best, and there is no reason for a small.
So what about Amazon? If you worked in Amazon, what do you say? Google is the best or mine is the best?
No, once those things are product. So once neural vision translation is there, like Google is going to do it. It's a generalized one. And the sense like there is no need for a small company to come and go and outperform Google. But in image processing,
so I'm not sure that statement is right. Yeah. So because again, context, particular use cases, you might need variants of the. Just like for image processing, you are seeing that there's an object detector module which you can deploy on Colab, Google, or whatever, and just use it. There are often variants based on the particular domain you want to use, small size objects, where you have to tune the network. So you slowly need to have a deeper understanding of what is going on there. Similarly here. So yeah. Okay, sorry.
The thing is, what are the things that, other than machine translation, what are the other things that we can do with neural network and NLP? Like other companies are focusing on.
There's only one paper, one guy has written Srivastava, that paper is dropout. And one single paper has so much impact on all the deep learning. No, so only one person can change.
So I think he's asking about application domains where.
Academic research is
Right.
But I'm saying about companies focus on NLP.
Yeah. So what you're asking is that I am not supposed to do self-driving cars. I'm not supposed to do translation. What is a simpler problem that they will not solve? And I can. It's a little. I'm.
I just want to know.
There are many things you have to.
Mostly like image processing, I can easily find applications where
You want to find applications. So text search will keep you busy for years. So again, you have to capture the meaning of the sentence. That guy has worked for a few years, I think. Yeah, you have to capture the meaning of the sentence, and you have to do a proper matching. Then, if you are done, then question answering. Again, you'll have Google and others to compete with, but that's a seriously hard problem. Yes. Yeah. Yeah. So the question answering, particular domain question answering. These chatbots are trying to solve these problems in a limited context. This is a domain. These are the questions. These are the answers. How do I remove the human from the loop as much as possible? Those kinds of things. Those are, yeah. I mean, there's so many domains of application that there'll be stuff. Things don't generalize from one domain to another. Until you have that, there's scope. Yeah. Good. Thank you. I'll just close this. Thank you for presence and asking questions. I hope you got something useful.